Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 4, Section 1, Chapter 6, Topic 5. Understanding Stress Life Equations for High Cycle Fatigue in Semiconductor Packaging. Introduction. High cycle fatigue is a critical failure mode in semiconductor packaging, where repeated cyclic loading can lead to cracks and ultimately device failure. Stress life equations, also known as SN curves, provide a fundamental framework for predicting the fatigue life of materials under cyclic loading conditions. This overview explores stress life equations in the context of semiconductor packaging, examining their principles, applications, limitations, and implications for reliability assessment. Principles of high cycle fatigue. High cycle fatigue occurs when materials undergo cyclic loading at stress levels below their yield strength but above their endurance limit. The fatigue process involves 3 stages. Crack initiation. Microscopic defects, such as inclusions, voids, or dislocations, act as stress concentrators, leading to crack initiation at critical locations in the material. Crack propagation. Cracks propagate incrementally with each loading cycle, driven by cyclic stresses and material degradation mechanisms, such as cyclic slip, dislocation movement, and crack tip plasticity. Final fracture. Cracks reach a critical size, resulting in catastrophic failure of the material, often characterized by sudden fracture and loss of structural integrity. Stress life equations, SN curves. Stress life equations, commonly represented as SN curves, quantify the relationship between stress amplitude, S, and the number of cycles to failure, N, for a given material under cyclic loading conditions. Key features of SN curves include slope. The slope of the SN curve represents the material's fatigue strength or endurance limit, indicating the stress level below which fatigue failure does not occur, even after an infinite number of cycles. Endurance limit. The endurance limit defines the maximum stress amplitude that a material can withstand indefinitely without fatigue failure, often expressed as a stress range or stress ratio. Fatigue life. The fatigue life corresponds to the number of cycles at which failure occurs for a given stress amplitude, typically plotted on a logarithmic scale against stress amplitude to produce an SN curve. Scatter. SN curves exhibit scatter due to material variability, loading conditions, surface finish, environmental factors, and other sources of uncertainty, necessitating statistical analysis for reliability assessment. Applications of stress life equations in semiconductor packaging. Stress life equations play a crucial role in predicting fatigue life and assessing the reliability of semiconductor packaging. Material selection. SN curves aid in selecting materials with appropriate fatigue properties, such as high fatigue strength, endurance limit, and resistance to crack initiation and propagation, to minimize fatigue-related failures in semiconductor packaging. Design optimization. SN curves inform design decisions, such as component geometries, load magnitudes, and stress concentrations, to reduce fatigue-induced stresses, extend fatigue life, and enhance package reliability. Fatigue testing. Experimental fatigue testing generates SN data for specific materials and loading conditions, validating predictive models, calibrating design parameters, and estimating fatigue life under real-world operating conditions. Reliability prediction. SN curves serve as inputs for reliability prediction models, such as finite element analysis, FEA, damage accumulation models, and probabilistic fatigue life estimation techniques, to assess the probability of fatigue failure and design robust semiconductor packages. Failure analysis. SN curves guide failure analysis investigations by comparing predicted fatigue life with observed failures, identifying root causes, and developing mitigation strategies to improve package reliability and durability. Thanks for watching. Please like, share, and subscribe.